Here in this video, we would like to talk about the design of a meter bridge and how can you understand it in comparison with a wheatstone bridge. Yeah. So first of all, what's a wheatstone bridge? Let's try to understand it. It's a quick revision, right? There are 4 resistors in a wheatstone bridge. P, Q, R and S. There are 4 junctions. Between 2 junctions, we connect a galvanometer. Between the other 2 junctions, we connect a battery. And there is a current flow, right? So, when the bridge is in a balanced state, the condition is that when the bridge is in balanced state, the resistors have a relation like P by Q equal to R by S. This is what we already know in a wheatstone bridge. But there is a practical problem in executing this wheatstone bridge. What is that is, how do you get that balance? You shall get the balance by varying any of these resistors or any one of the resistor. But when do you get that balance? We don't know. Therefore, you have to keep on altering the resistances, and it is practically very difficult to get the balance as you have keep on varying the resistance, and we may even miss it. We have done a video on that in the previous lesson on this topic. Please look into that. In the playlist, it shall be the previous of this video. So, instead of varying at least 2 resistances, let's use a concept like resistance of a wire is directly proportional to length and inversely proportional to area. So R equal to, with a proportionality constant rho called as specific resistance, rho L by A. So here in a wheatstone bridge, we take a wire. Here in a meter bridge, we take a wire of constant area of cross section. As area is constant, it's not a variable. For a given wire, rho is also constant. So R is directly proportional to L. So instead of taking these 2 resistors, R and S, we will take the length of that resistors. So what's the formula I can write now? When the meter bridge is balanced, P by Q of R, rho L1 by A. In the place of S also, we take a wire of same material having some different length, having same area of cross section. So this can be cancelled. So we can write a formula P by Q is equal to L1 by L2. Measuring lengths is much more simpler and comfortable than the measuring resistances. So meter bridge is a practical and simplified version of the wheatstone bridge. Then how do you arrange them? So that's also a point, right? So to measure these lengths, what do we do here practically is simply we take a meter wire and a meter scale. So this is the meter scale. On that we take a meter wire and fix it on this, right? So there's a meter wire here. What wire you take is manganese generally, or we can take a wire of a manganese or Constantan or something like nichrome. Why do we take that kind of wires? This kind of wire shall have low temperature coefficient. That means what? Even you vary the temperature, the resistance of this wire shall not vary significantly, and it shall have high resistivity. Therefore, measuring that becomes comfortable in the circuit. This is a meter scale then. It's exactly 1 meter or 100 centimeters. So with some kind of a wire, we divide this meter scale into two parts where you get a balance, where the galvanometer shows a zero deflection. So you get a balance in such a way that at this point you connect a galvanometer, and galvanometer is connected to the upper circuit that I will discuss in the later stage. So say for example, at this point if I get a balance, if this length is L from here to here, this remaining length will become totally 100 centimeters. This length becomes 100 minus L centimeters. So our formula will become P by Q equal to, this can be even further written like L by 100 minus L, where L is measured in centimeters, right? So we are going to simplify this. Instead of R and S, we have L and 100 minus L. So there must be something like somewhere P and Q. Where do we have that P and Q? It is simply like this. We have a P and Q here. This is the kind of a copper strip. We take the help of a copper strip for a connection because of its good conducting nature. And this is all the copper strip. We'll leave a gap here. Again here we'll leave a little gap here. This is again a copper strip. You might have seen this in our laboratory also, this kind of a arrangement, right? In one gap we connect a resistance box. We can keep a particular resistance, that is P, but we keep a resistance box, therefore we can do experimentation in different ways. So we connect a resistance box. In the other gap we connect a resistance X, which we can find out. So this P by Q can be further written like P by X equal to L by 100 minus L, because in the place of Q you have connected some unknown resistance. But anyway, if this galvanometer has to show zero deflection, it shall be connected from this point, from this copper wire. So this is connected this way, right, from that copper strip. Of course, this galvanometer is very sensitive. To protect that galvanometer from high currents, we connect a high resistance. That is simply for a protection sake. We will remove it as and when we are taking an approximate reading, accurate reading, right? But with this kind of circuit, there is no flow of current, obviously, because for the current, if the current has to flow, there shall be some kind of a battery. So we do connect a battery to the circuit too. From this manganese wire, we connect a battery of EMF E. We have a key where you can connect or disconnect it as and when it's required. Here you connect a rheostat so that you can vary the resistance and do the experiment in under different kind of conditions. So we extend this connection to the manganese wire like this. So this is how a kind of a setup is being made, right? So if you compare little carefully, here is your P, here is your P, and here is your P. Here is our Q. In the place of Q, R is directly proportional to L, so we have L. Here is your R. Here is your X in the place of R. Here is your S. In the place of S, you have 100 minus L. Here is your galvanometer. Here is your galvanometer. This is where your battery is. This is where your battery is. The other parts like key, rheostat, and resistance box are provided to provide a variety of readings in the experimentation. And a high resistance is connected to protect the galvanometer from higher currents. High series resistance is connected to the galvanometer so that we can protect that device. Now, using the meter bridge, we can now calculate the value of X. What's the value of that X is? P of 100 minus L by L. So you need to get that L where L is called as balancing length. So let us try to understand what do you mean by balancing length. If you observe the diagram carefully, this is some resistance. It is like your P, as I have mentioned already. This is your Q, like here. This is your R. This is your S. These are the two junctions. Say if you name this junction as B, this junction as D, this becomes the junctions of B and D. So you keep on varying this metal piece, which you call it like jockey. This is being called as jockey. So you lift the jockey and put it at a particular place on the meter scales manganese wire. Galvanometer shows certain deflection. You keep on varying the position of the jockey. At a particular position of the jockey, galvanometer shows a zero deflection. Then when the galvanometer shows a zero deflection, the bridge is in a balanced state. When the bridge is in balanced state, this condition comes into the picture, P by Q equal to R by S. Thus we can calculate the unknown resistance of a wire using the meter bridge. Of course, you can compare two resistors. Once after getting the resistance, you can use a formula R equal to rho L by A. In the place of R, X is what we have determined. A rho is something for a given, for this X there will be some kind of a rho. We can find out and substitute that value. L is the length of that wire X itself. Be careful, here L is the length of that wire. A is the area of cross section of that wire. By substituting that, we can even get the specific resistance. If you once get the value of X, length of that wire, area of cross section of that wire, using that we can also find row of wire. So using meter bridge, we can find resistance as well as the specific resistance of a wire, right? This is how briefly we can compare and explain the working of a meter bridge in comparison with a wheatstone bridge. Thank you for watching.